Hello, my name is Gregory Morris, and this is my machine learning stroke prediction project. Very briefly, I'm going to cover the project, the Jupyter Notebook, the implementation process, and the live product. This project was for the ML Zoom Camp provided by datatalks.club. I chose stroke prediction as it correlated with my Zombified project. Zombified is the idea of creating a health score as an aggregate of health inputs. Stroke is a major global health concern and would greatly impact this score. Let's take a look at the Jupyter Notebook. So I load in the data, and a library I like to use is DataPrep. DataPrep gives some quick statistics. It's going to, you see highlights right here, some things that you might want to take a look at. It gives some graphs, and it breaks down each of the features. It's a really great report. I would click on these tabs. However, I'm using Google Colab, and in Jupyter, that's fine. You can click on these tabs just fine. But Google Colab does not care for them, so I will not click on them. It will not be happy with us. But again, highlighting in red here, like, hey, you want to take a look at this? You have missing data, and various graphs. It even gives us a little bit of a correlation matrix here, and then a brief summary of statistics. Now, always after running data prep, I'm still going to go through the data in more detail and do some cleaning, maybe drop some columns, take a look at a deep dive into what type of data I have, some descriptive statistics, look at outliers, kind of get a feel for the data of what I'm looking at and where my concerns might be before I really start breaking down each of the features. And one of the first things I really noticed that was going to be a problem is the high imbalance. As you can see here, the 0 is non-stroke and 1 is stroke, and that percentage is really imbalanced, and that's a good thing in the real world. You don't want a high percentage of people having stroke, and I did find that it was representative of what you might expect globally. However, that's going to be a problem for the machine learning later on, and I'll talk more about how I dealt with that. Going through the features, one thing I noticed early on as well is the BMI. So for the BMI, there's a lot of missing values, and I had a hypothesis that the BMI for stroke positive patients would be significantly higher than the BMI for stroke negative patients. So I took a look at the averages, and stroke negative was 28.8, stroke positive was 30.5. In the real world, if you're talking to your doctor and you get a 28.8 or you get a 30.5, in all likelihood the doctor's probably going to give you very similar advice. So I really wasn't so sure on my hypothesis, but I wanted to be sure. So I did something called bootstrapping. Bootstrapping is where I take samples of the sample and get average and plot averages of each of those samples. And in this case, I took 15,000 samples and plotted 15,000 averages. And what I wanted to do then was look at 99.7%, see where 99.7% landed. And I know this looks a little different, but keep in mind I had to take some off the top and some off the bottom to get that mid-range of 99.7%. And what I found, and you can tell really quick looking at this graph, that hey, that 30.5%, 30.5 BMI, excuse me, is statistically significant. And so with that, I decided to fill in the uh, the missing values based on whether or not the patient was stroke positive or stroke negative. So the stroke negative patients, we get the average for stroke negative patients, and the stroke positive patients, we get the average for stroke positive patients for the missing values, that is. And this also uh, inspired the idea of a feature, obesity feature. I know that obesity is diagnosed at 30 or greater, and seeing that difference in the stroke positive patients made me think that we need another feature for obesity as an additional predictor that might help our model be a little more accurate. And again, I ran into a very similar issue with glucose. Average glucose, I assumed that it might be higher, and sure enough, it was. Stroke positive patients were significantly higher. However, just to keep with the rigors of it, I again bootstrapped it just to double check, and again, 99.7% of the data. And this one was just so far out. This was just, more just proof to myself. You knew just looking at it. And this feature is actually a little, it is interesting in that I had to create a feature called Clearly Diabetes. And the reason I use the word clearly diabetes is because diabetes is diagnosed with an average glucose of 140 or greater. However, just because you're below 140 doesn't mean you're not diabetic. You could be a type 1 that's in the honeymoon phase. So your pancreas is still producing insulin. So your average glucose might not have climbed that much and you're managing it really well. You might be a type 2 that's very well managed. You just have some spikes now and then. So we know that the people below 140 are a combination of not diabetic and well managed diabetics. However, anybody over 140 is clearly diabetic. Then, through the usual cleaning of the data, reviewing all the different features, I ran a final correlation matrix. Here you see a moderate, pretty strong moderate correlation of ever married in age. Not terribly surprising. When you create features based off of other features, you expect a high correlation. So obesity was a high correlated with BMI, and average glucose had a high correlation with clearly diabetes, excuse me. However, what was really strange here was this is a child in unknown smoking. And uh, there's probably a couple of reasons for that. If a physician has a patient come in and they're 2 years old, the physician's not going to be comfortable asking the parent, "Hey, does your child have a smoking habit or a smoking problem? Are they smoking? What's the how often are they smoking?" With patients, parents are going to be offended. It's just a weird question to ask. And is a child is such a range. Typically 18 is considered the adult, so you're certainly going to have some 15, 16, 17-year-olds that smoke. In the real world, I would reach out to the people who were collecting this data or inputting this data and bring this to their attention of how this might be a problem down the road of how we're collecting it and see if we could come up with maybe a better solution. I really would have expected this to have a higher correlation with never smoked. But given the sensitivity of the issue and how that could be offensive to a parent, I can understand how this came about. Our data is a little skewed, and that's the real world. It'd be nice if everything was a nice Gaussian distribution, but that's just not the reality of the world. Skewed data is just kind of what we have and what we have to work with. So let's get into the modeling. Go through the usual process of splitting our data. And first, I just decide let's run across a group of models and see what we get initially. And I have this confusion matrix. So here on this side is what the data is. So 0 means these are stroke negatives, and 1 means these are stroke positive. However, our predictions are stroke negative and stroke positive, and you can see immediately, and there's a pattern that's going to reoccur here of just how bad these models were, is that so a stroke positive patient, all of them were predicted as negative. Um, However, it was really great at stroke negative patients. Really great. Terrible trade-off. It's not what we want. You want to see 0 here, and you want to see 0 here. Though really, if you see 0 in either of these, you have to worry about overfitting, truthfully. But you want these numbers to be as low as possible. And sure enough, it's just terrible. They're really bad. None of these are good. And again, a lot of this comes from the imbalance that we had earlier on. As I mentioned, that just so few relatively to our data set, such a small percentage is stroke positive that the model's just struggling. It's really struggling. And even the best that it does is worse than what we end up with at the end. And let's get down. See, this is the best it could do. Not great, especially considering 15 out of the total of 60 it failed to predict. Not really happy with that. In the real world, you do expect a trade-off here in that, especially in healthcare, I've definitely heard this said in many meetings and that I've been in at work where they say, hey, if you're not capturing a lot of false positives, So you're predicting them as positive, but they end up not being. You're likely missing a lot of people who actually have whatever disease we happen to be talking about at the time, and in this case, stroke. So it's okay to have a high false positive in healthcare sometimes, because you're always going to run more testing. Like, oh, I'm sorry, we thought you had, say, a stroke. We were mistaken. We took a second look. Whereas what you don't want is to say, oh, no, you're not having a stroke, and send somebody home and then they die or something really bad happens. So this is generally the trade-off that we see quite often in healthcare. So I utilize something called SMOTE. Now, SMOTE can be a little controversial for some people, but what SMOTE does is it simulates part of the data to help bring that balance back. So in this case, I use SMOTE to simulate the stroke positive patients. Now, with SMOTE, you should only use it on training data, never on your prediction data, because you want your machine learning to be good at predicting real outcomes, not simulated outcomes. The goal is that these simulated outcomes will improve your actual predictions, and it does. You will see, however, in the end, there's a little bit of a drop, but it's better than anything we got previously. So we used Smote, retrained the models, and you see immediately it's already performing better. Now some of these they just struggled. A little bit better here. Terrible, terrible. I was expecting AdaBoost to do better. Really disappointed in it. Uh, and here, this actually ultimately ends up being our best model, but here this falls much better, way more into the acceptable range. Again, out of 60 patients, you don't really want to be missing 8 if you can avoid it. And in the real world, I think physicians do a better job than that. But this was a limited data set for this project. Um, so I was much happier with this. I was much happier with this. XGBoost, again, disappointed. Really expected better for XGBoost. Everybody loves it, but it struggled with this. So I grabbed some of my best performing ones, just for a little honesty here to see if I could tweak any of the features to make them a little bit better. And then we get into the model tuning. The tuning is where I was attempting to improve these models and see what we get. I took a look at feature importance, I looked at the data, and through all of it, unfortunately, I really couldn't improve much. Here we're going to take a look at our winning model, SVM, and looking at the hyperparameters. And I ran a grid search, pushing through. Of course, it's dangerous because grid search is just looking at numbers to tell you, all right, these are the best numbers. But when you're implementing something in general, even machine learning or otherwise, it's all about the value you get from it. And in this case, even if something had great numbers, the value is terrible. It's terrible. Look at it, it's failing to get all these stroke positive patients. However, this right here, the default model, let's see, what was this? Look at this, 88, 99. It looked great. These numbers are phenomenal. However, the 72 and 75% is way better. It's more practical. It's giving more value because it's just missing less stroke patients. And the goal here, the value that we're bringing, is predicting stroke. So this is what matters the most, is reducing this to as low as you get it. And it turned out that the default is the best, and sometimes that's just the way it works in machine learning. So we've selected our final model, or I selected my final model. Um, Now it's for deployment. So I use something called Bento ML. Bento ML is a product you can use to create containers, not unlike Docker. So you create a Docker container, but I was doing it through Bento ML. And so first I created a file for training, for what we just did, but for training the model in the future. You don't want to have to run an entire notebook again. If you want to run again on some clean data, you have some additional data sets, you just need a script to run. So I created a script. Then I saved the model from the notebook so we can utilize that in production. And when it gets to production, I then had to create a service. And when I thought about the service, I thought, okay, do I want to just return a percentage, or do I want to return some other value? And in this case, I took a look, I did some research, into how do physicians categorize your risk score, because that's more practical. If somebody gets a percentage, they might not know, is 5% good, is 15% good, where should I be looking at? And what I found was that we have low, moderate, and high risk. And low risk is under 10%, moderate is 10 to 15, and anything over 15% was high. So when I wrote the program that we're going to run later, you can see here it takes JSON input into the API, and then it'll just return based on the value. It's going to give us a low, moderate, or high. BentoML uses a YAML file. And this is our YAML file. Then from the command line, so this is just documented here, but in the command line, you would run a couple of simple commands, and this is one of the reasons to use BentoML. It packages everything quickly, it's easy to use. And now we have our container. So the next step is to get that container into production. So ultimately, this is our training script. This is our service that we're going to run. This is the input it's going to take. And there's our YAML. So what I did is I used AWS, and I uploaded it to the Elastic Container Registry. I had the command line, the AWS command line installed on my PC, so I was able to log in, run some commands, and which I do have documented in the GitHub, and upload it to Elastic Container Registry. Once you have it in Elastic Container Registry, you can then run Elastic Container Service. And what you do is you set up a service. You can see I call it SB Test 2. And with that service, you assign it a task. That task is going to run the service that we created earlier. It's going to run this. And ultimately, you end up with this. This is our API. And I have this open just so I can test it here. But realistically, this would be closed. It would only be allowed, an application would then send this input, whatever its input is, and then it would get back a parameter. So let's see, let's run that. We're going to execute, and you get stroke risk high, and that was the expected for what we submitted. And that is my stroke prediction project. Thank you very much.